And before we get started, I'm just going to go through a couple quick points. First, we're going to be doing a live Q&A at the end of this presentation and every subsequent presentation. So you can submit your questions in the drop-down on your GoToWebinar control panel. It says questions, so that's where those go. We try to get to as many as we can in the kind of 1 hour allotted for each presentation. If we can't get to your question, we will follow up via email. All questions are addressed anonymously. Quick disclaimer, all information discussed in this webinar is for education purposes only and should not be applied directly to the administration of any particular file or claim. This webinar is being recorded. We'll post it on our website, linked in the YouTube pages, so you can review them at your leisure or pass them along to colleagues or use them in meetings. Here's a big one. We're going to be sending everyone completion certificates via email next week. We will try and do this as quickly as possible. I know everyone's kind of champing at the bit to get their hours in, so we will do our best. If you're experiencing any technical difficulties, you can email our team at webinar@ocig.com, or you can use the aforementioned or before mentioned questions drop-down. Okay, let's get started. This is the 8th annual national tour. This year's topic is cat claims, more broadly speaking, extreme weather events. I don't want to go on for too long here and take time away from the actual experts. I'm just going to rattle off some quick stats that hopefully speak for themselves. So according to a report from Statistics Canada, between 1980 and 2008, catastrophic claims cost approximately $400 million annually. Since 2009, that number has jumped to roughly $2 billion a year on average. Of course, that means some years are higher than that even. That's how averages work, after all. In 2016, total losses amounted to nearly $6 billion. That was the year of the Fort McMurray wildfires. In 2013, we hit $3.87 billion. That was helped along by floods in Alberta and the Greater Toronto Area, as well as the December ice storm, also in the GTA. And then finally, last year, insured damage from natural catastrophes and severe weather events exceeded $3 billion. We experienced the hottest summer on record. That was punctuated by wildfires that burned more than 18.5 million hectares. That's another record. We had persistent summer droughts in the west. Those were contrasted by torrential downpours and deadly floods in Halifax and Quebec. So these events are happening with increased regularity and severity, and certainly warrant our attention in this presentation. So with that, I'm going to hand things off to our first presenters, Dino, Eduardo, and Paul. So Dino Mattei, senior consulting forensic engineer here at Origin and Cause. He has over 30 years of industry and academic experience. He's completed over 2,000 forensic investigations. His mechanical and materials engineering specialties include failure analysis, product liability, plumbing systems and component failures, oil spills, corrosion, metallurgical and fractography investigations, insurance fraud investigations, and personal injuries. He will be followed by Paul Amati, a forensic engineer in our Vancouver office. Paul is a licensed professional engineer in British Columbia and Alberta. His mechanical and materials engineering specialties include plumbing systems and component failures, corrosion-related failures, environmental degradation, HVAC system failures, personal injuries, product liability, and metallurgical and materials investigations. And finally, Eduardo Mary, fire protection practice lead and materials forensic engineer. He has over 20 years of experience in engineering failure investigations and industrial field experience. He's led over 1,500 forensic engineering investigations. He's been an expert witness and provided testimony in several judicial proceedings and hearings. His specialties include fire protection systems, mechanical, plumbing, and HVAC systems, product liability, personal injury, fuel oil installations, static equipment and O&G, and metallurgy and materials. So starting with Dino. Dino, please take it away.
Hello, everyone, and welcome to our webinar. Our topic today is quite interesting, and it hasn't been approached until today, and it's about insurance claims associated with weather-related conditions, catastrophic failures, and we are going to present a few interesting cases that we ran along, and I hope you'll find them interesting. And at the end of the session, feel free to ask us any questions. I divided my presentation in 3 sections, and the first one is dealing with the heavy rains. We all know when heavy rain occurred, water penetrates everywhere, water travels easy, and it can cause significant damage. The typical claims that we encounter when there is a heavy rain are sump pump malfunctions, roof drain pipe failures, water infiltration, sewage backup, and as you will see later, the unusual. The first case study refers to a residential place here in Ontario. It was a small home, and during severe storm, winds and rain, a tree fell onto the roof of the house. It damaged a portion of the roof, and it left a portion of the attic space exposed to the environment. In that attic space, there was a sections of an air duct, and it was damaged by water. As you can see in this image, the gray component is a sections of the air duct, which was originally made from galvanized steel. It should have looked like, it should have exhibit a shiny metallic appearance. However, because of the oxidation, it looks dull and it has those white deposits. The homeowner requested the insurance company to repair the entire duct conduit inside the house, claiming that because the attic space was exposed to an environment, it caused significant damage. There was no doubt that the section in the attic space that was exposed was damaged by being exposed to environment. However, the insurance company was not so sure about the rest of the air duct, so they contacted us and asked us to conduct a thorough investigation of the duct in this particular home. So we were equipped with a snake camera, and we went from the roof to the basement and inspected the entire conduit. I'm not going to show all the pictures that were taken. I'm just going to show a few relevant ones. So we started in the attic space, and you can see in this image, the duct is compromised by exposure to water. Further down, the duct seems to be clean. Considering the age of the house, 40 to 50 years, the condition of the duct is exceptionally good. There is no evidence of significant corrosion or other type of degradation. Moreover, in one section, there are spider webs, so when you have water, you don't have spider webs. I went further down to the basement, and as you can see, the duct in the basement seems to be in good shape, except for a small section which was severely corroded and stained. A close-up view of the degraded section is in the next slide, and you can see the severity of the degradation. Upon further examination of the basement, I discovered that the localized degraded section of the duct was under the drain pipe from the powder room. What we see here is the drain pipe, the elbow from the powder room, which runs on top of the duct. The wood around the flange is rotten, the flange is corroded and is broken. There were some attempts to repair, as you can see by the fresh screws in the floor. So what happened here is the flange degraded, the floor degraded. So every time the toilet was flushed, some of the products ended up escaping and ending up on the duct. So there was no damage associated with the storm or with a fallen tree. It was a historical degradation, and it was negligence from the part of the homeowner. At the end of the day, based on my comments and observations, the insurance company decided to compensate for the damaged duct in the attic space. However, no compensations for the historic damage to the remainder of the duct. Ice can cause a lot of damage inside the pipes because it expands, water expands 9% upon freezing. Ice can cause damage on the outside to the roofs and other structures. Typical damage claims that we generally see coming from the formation of ice are frozen sprinkler systems, collapsed structures, frozen pipes, and other plumbing fixtures on appliances. Freezing in homes can occur if a furnace malfunctions. This can happen if the air intake is blocked by ice formation. So basically the furnace is, for the lack of other word, suffocated. It has no air to breathe, it cannot function, and it eventually stops. This is happening quite frequent when there is ice formed on the intake or snow accumulation. Ice can cause damage on heat pumps even during outside the cold season. I was asked numerous times, how come a heat pump can freeze when it's summer? This can happen if the refrigerant level is too low, the evaporator coil is dirty, or there is poor airflow. I'm sure you all saw ice on the air conditioning unit outside your home during summertime. This means that the air conditioning unit needs to be looked after. So freezing during summertime is quite possible. The next case study that I'm going to talk about is associated with the distance marker installed on a rowing course. On rowing courses, there are distance markers installed every 500 meters starting from start to finish that helps the participants to know exactly where they are. This picture shows a typical distance marker, and it's actually the incident one. It was located 1,000 meters away from the start line. And although it looks like a small structure, is actually massive, and it weighs several tons. On a march a few years ago, this particular distance marker simply disappeared from the lake. One day it was there, the next day people walking in the park noticed it was gone. What was left visible from the surface of the lake is one leg. The yellow ball and the red flag are installed here to prevent accidents because it was very close to the surface, and to prevent injuries. It was marked so the participants on the rowing course could bypass it. The insurance company retained us to determine what happened. And the thing is, they were not necessarily looking for subrogation because the structure was very old. What they were looking for was to determine whether this was an intentional act, it was wear and tear, or it was an act of God, because depending on the findings, there was coverage or there was no coverage. So we were retained to investigate what happened. The problem was that the entire structure was below the surface of the water and there was nothing visible. So we attended the site to retrieve the structure. This is me geared up, ready to jump and retrieve the platform from the bottom of the lake. Just kidding. We retained the services of professional divers who helped us to retrieve the structure. The job was a very difficult one. It was challenging because the visibility underwater was close to zero. There were some currents and there were some metal remnants which nobody knew how they were arranged. As you can see, the diver has safety features like a lifeline, 2 breathing lines, a communication line. So with their help, the remainder of the structure was fished out from the lake and it was brought to the shore. The incident occurred in March and we retrieved the platform in September. So the platform remained submerged underwater for several months, condition which changed its appearance. The platform was brought ashore and we looked at it. It has 4 legs and you can see 2 of them were severed. One was bent and mechanically deformed, and the 4th one is in the shadow and it's not visible, but it was damaged as well. Because it was staying submerged underwater for such an extended period of time, the structure was covered in algae and mussels. It was a difficult task to look at the fracture surface because of severe oxidation and degradation. We cut small sections from the legs and we tried to determine what could happen to the platform that it collapsed. Cleaning was very tedious because, as I said, the extensive damage to the fracture surface. We used special chemicals and we managed to look at the fracture surface. This is the appearance of the fracture surface, of the small sections of the fracture surface before being cleaned. After ultrasonic cleaning, we took the samples to be examined under a powerful microscope called scanning electron microscope. This microscope allows us to examine fracture surface and features at higher magnification. The platform was made of carbon steel, which is the most common steel that one can encounter. This carbon steel, when it's subjected to the stress, usually fails in a ductile manner. It means that it has some plastic deformation, some yielding before the final fracture. However, in this particular instance, when I looked at the fracture surface under higher magnification, I saw typical features that are associated with brittle failure. What it means, it was no deformation. It was the fracture was like a glass fracture. It was all of a sudden without any plastic deformation. And this tells me, and also we looked at the microstructure. Every material is made out of grains, like ingredients in a food. You put ingredients together and you get the final mixture. Same thing applies to materials and alloys, and carbon steel is one of the simple alloy which is consisting of 2 phases. It was nothing wrong with the microstructure. No gross metallurgical deficiencies were observed. So there was nothing wrong with the material. However, it failed in a brittle manner, which it shouldn't. I checked the weather reports, the historical weather in the area at the time the platform collapsed, and I found out that it was very cold and there were strong winds. So based on an analysis on the condition of the platform, the fracture surface, and weather conditions, I concluded that the incident happened because of ice impingement. In other words, the lake was covered in a thick layer of ice, and because of the winds, the ice was pushed against the legs of the platform, making it to collapse. So the conclusion at the end of the day was that there was no intentional act, it was no wear and tear, there was no evidence of progressive fatigue, it was an act of God. The platform was overstressed by ice impingement. So based on that conclusion, the platform was replaced, and there was coverage for this claim. The next case, it's an interesting one, and it involves a freezing rays, ice accumulation, and strong winds. It's an incident which occurred at a golf range located somewhere east of Toronto. This is a Google Maps picture of that golf range before the incident. As you can see, two sides of the golf range are protected by a netting. There are long poles and there is some plastic netting in between to protect the surrounding businesses from balls flying all over the place. During a severe storm and winds, the poles and netting collapsed on the close by building, causing significant damage. This is an image that was taken from CTV Toronto, because by the time we were assigned to this claim, the site was cleared for safety reasons. At that time, there were strong winds and it was freezing rain, and you can see on the ground ice pellets. By the time we arrived at the site, it was nice and shiny, sunny, and this is how we saw the site. You can see that it was only one side of the netting that collapsed. The other one remained intact. The steel poles holding the nets were brought in from California and were welded from 3 sections, and they were welded by the manufacturer, not on site. So they were just planted here. They were brought already welded. They were planted here, and then the netting was connected. What was common is that the failure occurred between the bottom and the middle section on all the poles. This is one bolt holding the netting, and it was also fractured. This is a typical fracture surface from one of the poles. It was a joint examination with other parties, and we jointly selected the samples for further lab examination. The lab examination included visual and stereo microscopy in as-is condition and clean condition, examination of the fracture surface under scanning electron microscope, metallography to see whether the microstructure is sound, hardness survey to see whether the heat treatment of the steel was proper, chemical analysis to determine whether the chemistry is conform with the designer specs, and also to check the weldability of the steel. These are a few samples that we selected for examination. And looking under the stereo microscope, we saw large voids in the weld. These are undesirable features because they act as stress concentrators and will diminish the load carrying capability of the weld. Further examination revealed not only the large porosity, but also inclusions, which are also undesirable in a weld. Looking at a fracture surface similar to the one on the rowing marker, we saw brittle failure, which indicated a problem with the weld. Some of the welds failed as intended in a ductile manner, and this is a typical appearance of a ductile failure. although there are some voids present as well. Further metallurgical examination in the cross-section revealed porosity below the fracture surface. This is the fracture surface on top, and those dark features here represent porosity, which are, as I mentioned, undesirable. The weld between the sections should have been showing full penetration. However, it shows only a shallow penetration, so the weld was substandard. We conducted microharness survey, chemical analysis, and weldability. We did not find any significant difference between the weld material and the parent material. The steel was fit for the application, and it was weldable. It must be said that some alloying elements will make welding more difficult or impossible. In this particular case, the material was weldable, so the conclusion was the failure appeared to have occurred by dynamic overload at the welds. It was not only the ice formation on the netting, it was also the drag that was caused by the wind. And the conclusion was that the failure was possible because of a combination of factors like undesirable defects in the weld associated with weather conditions. People were asking, the insurance company asked me, how come only one side of the netting collapsed and the other one did not? If I move back to this image, you can see this is the side of the netting that collapsed entirely, and this one survived. This section runs north to south, and this one runs east to west. And the winds were blowing almost east to west. So the wind was blowing perpendicular to the netting here on this side, and it was running parallel to the netting on the east-west side. So it was a lot of stress accumulated on the north-south section compared to east-west section, and this explains why it's survived. Having said this, I'm going to pass on the mic to my colleague Paul, who will present some interesting cases. And thank you for listening.
Thanks, Dinu. Yeah, thanks again, Dinu. So my name is Paul Amati. I'm the mechanical and materials engineer in Vancouver and Western Canada. So I'll be discussing some failures related to oil filters and oil storage tanks. To start, we're going to look at a specific case study involving a diesel fuel oil filter. And this case came to us after a bout of extreme cold. Let's take a closer look at some photos related to our case study of the oil filter. To be specific, this is a filter for a residential oil tank. And when I say residential oil filter, your first thought might be that these components are relatively simple and a failed one couldn't possibly cause enough damage to be worthwhile to investigate. Well, that's not the case. Some oil tanks can hold up to 900 liters of oil. So imagine if the filter fails or if there are any other issues with the tank, how will the property be affected if hundreds of liters of oil are released all of a sudden? And the cleanup costs can be in the hundreds of thousands of dollars. And in some cases, the home or the property will just get demolished as a result. Interesting enough, if the damage to the environment is extensive, the contaminated soil has to be excavated for remediation. So if you're in Ontario, the closest place to treat the soil is actually in Quebec. So you can imagine the costs related to excavating and transporting soil from Ontario all the way over to Quebec. But yeah, I digress. Let's get back to our case study of this residential oil filter. In this image, you can see the failed filter that was received a few weeks after the incident had occurred. Unfortunately, no site examination was conducted at the time of the failure, which limits some of our immediate observations. The filter arrived with the lid and the canister separated, as we can see in this picture. And it's always an essential step for us to note the condition of components when we receive them. And an important observation was that the cartridge inside the filter was still attached. And this cartridge showed signs of darkening, which indicates that it had not been replaced for a significant period. So regular maintenance and timely replacement of oil filters are important to prevent issues down the line during operation. So continuing with our case study photos, we have a close-up of the manufacturer label on the filter. So we can see here highlighted on the label, the manufacturer provides clear instructions for the maintenance. So the label says the cartridge must be replaced when it's clogged or at the beginning of the heating season. And these instructions sort of emphasize the importance of regular maintenance, ensuring that the oil filter functions properly. And the label's warning points to something important, which is that neglecting to replace the cartridge as recommended can lead to issues like clogging or reduced efficiency. And in our case study, the darkened cartridge that we saw earlier in the previous slide showed that it hadn't been replaced for a considerable time. Next, we have a side-by-side comparison of the incident fuel filter and a canister that we retrieved or procured as an exemplar. So the canister on the right is the incident one, while the one on the left here is the standard that we used for comparison, the exemplar. And a noticeable difference between the two canisters is the size of this hole at the bottom. The incident canister obviously has a larger hole, and this suggests that it might have experienced an abnormal pressure buildup or some type of physical damage. In this slide, we're continuing the comparison between the incident fuel filter and the exemplar, but this time we're focusing a little bit more on the interior of the canisters. And on the left, again, is the exemplar, which appears relatively clean. But on the right side, we see the interior of the incident canister, which has started to show signs of corrosion activity. So this evidence of corrosion indicates that the canister was likely exposed to moisture or other corrosive elements over an extended period of time. And in this slide, we have a detailed view of the bottom of the fuel filter canister, focusing on this circular piece that became separated from the bottom. So this slide shows the circular piece sort of side by side with the large hole that it left behind. So the canister was subjected to such a force that the bottom mounting bolt was pulled out against the canister's bottom, which cut out this circular section. And this type of forceful action indicates a significant impact or pressure that exceeded the normal operating conditions. Typically, the pressure at the bottom of a fuel oil tank is around 5 psi. Such pressure, or this amount of pressure, isn't enough to cause the damage that we see here. which is cutting out the bottom and even bending the material. So we can infer from that that an abnormal event occurred. And given the circumstances, and after ruling out manufacturing deficiencies, freezing really emerged as the most plausible cause for this failure. This photo was taken by the homeowner at the time the oil spill was discovered, and it provides a real-world type of context to the incident that we've been looking at. In the image, you can see the setup of the fuel oil tank and the filter system. And notice this red oil filter is what we're looking at. And what it is a type of inline filter at the bottom of an oil storage tank. So this photo is a real interesting one. At first glance, you think that at the bottom of the filter here, and you think it's actually still attached, but really that's not the case. This bottom is actually a block of ice, and the filter covering is on the bottom left here. So it's a little bit of a tricky image. And this was an important picture for the investigation because soon after the weather changed and this caused the ice block here to melt, which would have made determining the cause much more difficult. Sorry about that. Right, so in oil installations, water can accumulate due to condensation, and we know that water is heavier than oil, so it makes its way to the bottom of the tank. And once the oil is set to run out of the tank towards the furnace, because the water is at the bottom, water will run out first and then accumulate in the filter. So the homeowner should have checked for stagnant water, but apparently hadn't done this for at least 2 years. And if we remember, the manufacturer label attached to the filter mentioned that it needed to be maintained and cleaned when clogged or before the onset of the heating season. So if you don't empty the filter from water for a long period of time, more and more water accumulates. And if the weather conditions are right, it will freeze. So in this slide, we see another important aspect of these systems, which is the fuel oil tank itself. This photo shows a tank after it had toppled over because of high winds. And fuel oil tanks are large and they're heavy, especially when they're full, but they can still be vulnerable to environmental forces, such as strong winds. In this instance, the tank wasn't adequately anchored, which led to its toppling over. And proper anchoring is important, really, to ensure that tanks remain secure in all types of weather conditions. This means using appropriate anchoring systems that can withstand environmental forces and prevent the tank from moving or falling over. And by ensuring that tanks are correctly anchored and regularly inspecting the anchorage, we can prevent these accidents and maintain the safety of the fuel tanks. Here's a bonus one, actually. Just since we're on the topic of oil filters, it still has to do with the environment. I believe personally that it has something to do with the weather, but I will let you be the judge on that one. So this is a different example of how failures can occur in these types of oil systems. And the vent pipe of an indoor oil tank. The oil spill occurred because the delivery driver didn't hear the vent whistle, which is an indicator of when the tank is full. So vent whistles are installed on vent pipes of fuel oil tanks, and their design is to produce a type of whistling sound as air escapes from the tank during the filling process. So when the tank is nearly full, the rising oil level blocks the vent pipe, and this causes the whistling sound to stop, which serves as a type of audible signal to the delivery person that, hey, the tank is full and you should stop adding fuel to prevent overfilling. So you can imagine, without the whistle functioning, the driver unknowingly overfilled the tank, which led to an oil spill. And the reason is very clearly shown in this photo. Bees had built a nest inside of the vent pipe, which obstructed it and prevented the vent whistle from working as intended. And this incident more or less highlights how even a small and seemingly insignificant issue like a bee's nest can have significant consequences. And it's important to note, preventing these types of failures, it's essential to regularly inspect and maintain all of the components of the fuel system, including the vent pipes. So we need to ensure that these pathways are clear and functional, which is very important for the safe operation of the system. And as required by the code, they have to be inspected every year. And on top of that, the delivery drivers are supposed to follow certain procedures that are stipulated by the B139 code. But just on this, I'm going to pass it over to my very good colleague, Eduardo, to continue with another case study related to oil fuel tanks.
Thanks everyone for joining. Thank you, Paul, for that introduction there. And yes, I will be speaking later on about fuel oil tanks, so stay tuned. My talk today is about flooding, and that's originating from rainstorms, or very strong rainstorms, if you would. The type of losses we normally investigate during or after flooding events include flooded basements and parking garages, sewer backup, fuel spills, electrical fires, believe it or not, yes, vehicle water damage, that's easy to see, and structural damage to building foundations. In Canada, as Mark said, we've seen a number of increased losses due to severe weather, including flooding. Many of you may remember the flooding that occurred in Toronto in 2013. Back then, the city received approximately 1.5 meters of rain, which poured in under 19 minutes. So you can imagine that approximately equals to the entire amount of rain that would fall in the city in the month of July in that short period of time. And obviously we saw the consequences of that, including this train that was stranded in flood waters, and the passengers had to be evacuated via small boats. We also saw a number of homes and businesses that were affected where their basements flooded. And obviously the claims that arise from those losses. In Canada, there are many examples to share. I'm just picking up on a few. Merritt, BC in 2021, all 7,000 residents had to be evacuated, and just less than 1,000 homes were damaged, 300 of which had to be partially or totally demolished. You can imagine the devastation. That brings me to my first case study, and this speaks of an event that occurred in Ottawa on 2023, where heavy rainstorms flooded several areas of the city, and the subject building was heavily damaged, as you can see from this one photo. The main floor was inundated, and the basement, which was fully occupied, was full of water all the way to the top, so significant damages to elevators, business interruption, and a number of things around the building, in and around the building. So one of the contributory factors to a flooding loss like this has to do with sump pumps, which are installed at the lowest level of a building and are meant to remove water, either groundwater or rainwater, depending on the installation and the design. There's multiple options that we can see and find. In this case, that particular building had multiple sump pumps, and well, we saw some failures. There was also obviously other contributory factors that created these loss. But in general, most residential and commercial sump pumps are one of these two types, either submersible and pedestal pumps. They both operate under a similar principle. There's a motor, a pump, and a float switch that activates the pump either to turn on or off. Inside the motor for these pumps, there are some components that can be damaged, including the start capacitor. And these electronic components, when they fail, the pump simply wouldn't start. And again, I always tell my clients to remember that these pumps are mechanical components and they're bound to fail. So there's always the need to have redundancies in the systems. But in any case, this is one of the reasons why they start, why they fail. If the pumps are relatively new, then there's no good reason for them to fail, and we can move ahead and examine them. If they are close to their lifespan, then the decision rests on the insurance company and the adjusters to whether to move forward with additional work and possible subrogation. One of the other reasons, or one of the most common reasons of failure, involve the float switch that I'm showing here. And on the right, I'm showing an X-ray of that particular float switch. Multiple reasons for them to fail, including installation. Say the tether line is too short or too long. They catch with other equipment in the sump pit, or there's always vibration in this system, so they're allowed to they're not restrained properly, and they're allowed to move and get caught with the walls of the pit or something else. But let's look at this particular case. So this one shows and let me just walk you through what the anatomy of that float switch is. So it's very, very simple. There's a ball inside that moves up and down when the position of the switch changes, and that activates a mechanical lever, and that lever opens or closes an electrical circuit. And that electrical circuit is in a micro switch or a switch. And that switch or micro switch is what I'm showing here on the right. And in this particular case, you can see there is some melting, some charring. It looks like there was some either a small fire or a lot of heat being produced there, and some of the components are damaged and out of place. So if we look in more detail in this particular case, we see that on the picture on the right, there is one pad or contact pad for the electrical contactor. And then on the top part of that image, there is a shadow showing where another pad should have been. And this basically tells us that one of the pads disconnected or was not properly attached to begin with and came off. Obviously, if you have a loose metallic component in a system like this, then it's most likely that it's going to contact something and create a short circuit. And that's most likely what happened here. We did find the missing pad. It's here. This is the back side where it's was supposed to be welded to the tab. And again, in this case, it was clearly a manufacturing issue. This was not a very old pump. And we were lucky to find all the pieces and able to identify the issue. Now, it's also interesting to keep in mind that from a technical point of view, we could have gone a lot further down that road and find whether the materials were proper, the welding was proper. And that typically happens when we have different manufacturers manufacturing the individual components that go inside. In this case, that wasn't necessary, but just keep that in mind in case it's needed for your claims down the road. The second sump pump that we examined had a different mechanism of failure and involving the same microswitch or a similar microswitch. In this case, we're going to be looking at this white tip at the top of the black microswitch on the image on the right. And that tab or lever, as I call it, is just a mechanical lever that allows the microswitch to activate once that, remember that ball that is in the float switch, when that ball goes up and down. And if we look at the close-up picture, the magnification here on the right, we can see the appearance of that plastic lever has changed, and it looks like a popcorn basically, and that tells us there's been some type of degradation to it. And this is very interesting because it's a polymer that's encapsulated in a sealed float switch. So there's no water or any other elements that are going in or out. And so there's a question as to what caused that and whether it is a manufacturing issue or something else. So we open the micro switch. You can see here clearly that that tab is, or that lever is has been affected, but only the section of the lever that is outside the micro switch. Remember that this micro switch is inside the sealed float switch, but it's interesting that only that section of the lever is affected. So at this point, we obviously have to understand why is that in order to try to find the root cause. And so we did some analysis on that very tip that's discolored and damaged, and as well as on the core of the material away from that damage. What we found during the FTIR analysis of that polymer is around here, around the 1500, 1700 weight number mark, we found some evidence of degradation. We can see that highlighted here, where these two peaks that I'm highlighting here are clear evidence of structural degradation in that polymer. And basically that tells us that something inside had damaged that material. Now, when we do the analysis on something like this, we know that there's no water coming into the float switch that could have done this. And it doesn't look like it's a liquid because there's no damage anywhere else. So our analysis pointed to a possible off-gas from either some of the glues used to seal the float switch or some of the other components that were off-gassing inside. And at that point, we had enough evidence to close our file, and our client was able to recuperate on that claim. But we had the opportunity, or we could have done additional testing, such as GCMS, in order to understand what's the particular type of material or compound that was causing that damage, and then further prove it that it was some off-gassing material. So in terms of lessons, conclusions and lessons learned for this case, remember that we had multiple contributory factors, including manufacturing defects. And as a result of that, our client received a settlement and our file was closed. Also, we learned that, or we want to share that it's always important to have or give an opportunity to inspect the scene and all possible contributory pieces of evidence, because that is critical for not only for your side, but also the other side to better understand the situation and for everyone to be able to be on the same page when doing an analysis. And also remember that when presented with one cause of loss, it's important for you to always confirm if other possible causes were eliminated, and that will give you an advantage moving forward on your claim. I have a second case study, and this one is related to a fuel oil tank. I'm just going to continue on this trend that my colleague Paul started. And this one in particular, again, it relates back to flooding or severe rain causing flooding. And the claim happened in Marks Day, Ontario in 2015, or the loss. And the claim was related to the tank overturning due to inadequate installation. And these happened during flooding. So the state law claim in this case was sent to our insured after all repairs had been completed. And that's key to the investigation because we didn't have access to any of that evidence firsthand. Also, they focused on the standard of care for their position and indicating that the installer, which was our client's insured, had done a poor job, and we were tasked to understanding whether that was the case or not. So this investigation went back and forth over several years, and I personally wrote 3 reports. I had some consultants on the file from my company, and we were able to do a complete analysis, but I'm just going to summarize some of the important points here. And in the plaintiff's position or expert report, they claimed that the subject property was very close to marshlands, ponds, and some creeks. And so as a result of that severe thunderstorm that happened around that time, the subject property flooded and the tank floated, overturned, and spilled. We were able to do some simulations and or review some simulations, and this was a 1,000-year event. So basically, this would have been the most rain this area would have received in a very, very long time. And basically, the simulation proved that the subject property was not subject to flooding during this very heavy flooding event, or a simulated very heavy flooding event. And that led us to, in a way, show that the installation complied with the requirements of the code. Remember, the code, in this case, ESA B139, is one of the, or the industry standard applicable for the installation. And remember that the claimant, plaintiff claimed that the tank should have been anchored to the concrete floor in the basement. But the reality is that the code applicable at that time, and that's very important to find out exactly what's the code that's applicable, did not require the tanks to be bolted or anchored to the floor. Because of the lack of information we had on this file, we took some maps, pictures from maps, including this one that clearly show the property was not in a floodplain or on a low point. And there were other factors to consider, such as other comprehensive inspection reports that were done on the installation after the installer, our clients are insured, had finished the work, and over the years. And also one of the big points in this one, this investigation, was whether the area was subject to was a part of a floodplain or flooding was anticipated. And again, the installer at the time only had to comply with this particular clause in the code if he knew or was informed that this area was a floodplain or was expected or anticipated to be flooded during a rainstorm, heavy rainstorm. So some of the photos we found in the documents from this location show, a basement in a rural property, unfinished basement, concrete floors. There was a sump pump in that sump pit, and everything pointed out to the basement uh, not being completely dry, and that's very normal for a rural building, because you would expect that some water may be, or some groundwater may be coming in, and that's why you have the sump pumps there. In this case, there were 2 sump pumps, which indicates the homeowner had that provision to, in case something happened to one, he had a backup pump, which was good. And as you may know, in many of these fuel oil losses, the cost can rake up quickly. In this case, part of the house was demolished, the foundation had to be excavated just to remove all the oil from the soil. And so one of the things that we want to convey, the messages we want to convey here, is that if you must deal with one of such claims, and again, these claims are not does not occur as often as they did approximately 10 years ago. You have to make sure that it gets investigated as soon as possible and by the right people. So in terms of conclusions and lessons learned from this case study, we helped in getting a position where our insured was not liable, and our case was closed. And I just want to point out to the fact that timing of notices to third parties is critical. If you have a chance, give an opportunity for the other parties to inspect the scene or the installation prior to major repairs being done. Obviously, there has to be some sort of a remediation started right away, but try to give opportunity to other parties to get some of the evidence as well. And these will be very helpful for everyone, because we're not, as experts, we're not depending on pictures that were taken by someone else. We often don't have notes or any other points of references other than just those pictures. And if they're not great, then we are very limited. And also note that third-party expert reports need to be very carefully reviewed by your own expert. In this particular case, the plaintiff's initial expert report appeared to be very solid, but during our review, we found significant errors in their evidence and premise. And that's it for me today. I hope you enjoyed it. And any questions, Mark's going to take care of it.
Thank you very much, Eduardo. Yes, this is the time for questions. There's a couple already. I've got one here for Dinu. The air intake to the furnace, the elbow is sometimes up and others facing down. Is there a correct way for this elbow to face, up or down?
Should the end face of the elbow should be perpendicular to the ground. So if it's sloped or it has a curve downwards, ice can accumulate, and if it's the other way, rainwater can get in.
Okay, fantastic. Eduardo, this one's for you. In your first case study, you kind of referenced the age of sump pumps as a possible cause of failure. So what is the average lifespan of a sump pump?
That's a great question, and I get that question many times a year when I present to other clients. It really depends. It really depends on how much the pump operates. So if there's high water table and the pump operates multiple times a day, then it's going to last less time than if it operates once or twice a week. In general terms, I would say a sump pump that is active or relatively very active should be replaced after 5 years. Typical or average lifespan is 10 years.
Okay, thank you. Wait for some more questions to come in, but the idea was to take a bit of a break, so about 5 minutes. Now we're going to come back in 10 minutes with Nabi Guderte, who's a structural engineer, and he's going to be talking about some claims he's investigated in the primarily the East Coast. Okay, so let's take 5, and we'll be right back. And I'm just going to mention too, after Nabi's presentation, we'll take a break for lunch, 30 minutes, and then we'll resume. Just so if people need to kind of organize their days, that's the plan. Okay. Thank you, Paul. Thank you, Dinu. Thank you, Eduardo.
Thank you.
Oh, sorry. Question just came in. Let's do this one since it's here. When large storms are forecasted in rural areas, does securing outdoor fuel tanks take a higher priority amongst other exposures?
Thanks for the question. It's Eduardo here. So the code requires tanks that are subject to high wind areas to be strapped down. So it's not there's no requirement for you or anyone to be securing tanks prior to storms. They have to be done, or this has to be done during the installation of the system. There are some areas there are known areas and referenced areas by Environment Canada that are subject to high winds. So those areas require a strapping of the tanks or better anchoring of the tank. In some other areas, it might be just local knowledge of the local installers, homeowners, or the authority having jurisdiction in the area.
Okay, great answer. Thank you very much.